as Graham said, it's going to be super condensed. And on the Indico web page, we have different links. If you go to Run on Binder and click on that, well, it's going to take a while to open. So we're going to leave it there. In the meantime, there are other links. This setup link, which is has different options if you want to run this tutorial. So you can use Binder, or you can use Google Colab if you have any problem with Binder, or you can use Swan if you have access or you have a SEN account. For Google Colab, you need a Gmail account, and probably the easiest one is Binder. And or if you want to run the everything locally, you can just use Anaconda, and it's gonna work well. Also, there is another link here. This is Matplotlib for high energy physics, and I'm gonna go through that in a moment. But you can see also here the setup I just mentioned, and every episode or chapter of this tutorial. I'm not gonna go cover everything, but you can. This is publicly available, so you can access all this material. And the last one is the GitHub repo, which I'm gonna invite you if you see any issue in this material, you can contribute. It's not complicated, so you can open an issue here, or you just can open a PR, and we'll be happy to see any contribution from you. So I think this is still opening. Okay. Oh, it was fast. It's okay. In the meantime, let me just introduce this tutorial. So this Matplotlib tutorial is based on the material that we have been developing during the last year in the HSF Training working group. And this is going to be a very short introduction to Matplotlib, and I'm going to try to go through an analysis using some data from ATLAS open data, and also from CMS to get some publishable plots. And if I have enough time, I'm going to go through mplhep, a Matplotlib wrapper, used in high energy physics as well. And again, this tutorial is going to be a subset of the complete Matplotlib training module. We already used this material last April in the first Matplotlib for high energy physics workshop. We had 100 students registered. And well, this material is constantly, we're trying to constantly improve this material. So again, if you want to contribute, we'll be happy to have you with us. So the expected knowledge is, if you have a beginner level understanding of Python, that's enough. Some knowledge of Scikit-HEP modules is helpful, but it's not essential. And the idea in the first part, I'm gonna briefly introduce Matplotlib. And so the idea there is to get or to learn the basics of Matplotlib and learn how to manipulate the elements of a plot using Matplotlib. And then in the second part, we're gonna use ATLAS open data, and we're gonna try to get this plot. And this plot is the plot for a golden channel for the Higgs decaying into 4 leptons, the Higgs decaying into 2 C bosons, and these 2 C bosons into 4 leptons. So the idea is to get this plot using Matplotlib. And then if I have enough time, The idea is to use mplhep and some CMS open data to get this plot, which is basically the same one here. Again, for the golden channel, the Higgs decaying into 4 leptons, the Higgs into 2 C bosons, and then to 2 leptons. So that's the idea of this tutorial. So let me go back to the binder. Okay, it's already here. So, okay, let me move this. Okay, and then we close this window. I'm gonna open a new notebook here. And again, as I said, this is the material. It's publicly available. It's in the HSF Software Training Center webpage. So you can access this webpage, and you can have all the material here, and also all the people who are contributing to this material right now. So let's start with the setup. I'm sorry, the setup, no, with the introduction. And as I said, the idea here is to understand the basics of Matplotlib and learn how to manipulate the elements of a plot. So the first thing that we're going to do here is just to import the libraries that we're going to use during this first part of the tutorial. So we're going to import Matplotlib .pyplot, sorry, as PLT, and also I'm going to import NumPy. I'm going to use it later to generate some data, and then we're going to run this. So the simplest way to create a figure in Matplotlib is to use pyplot subplot, pyplot.subplot. So basically we have this. If we pyplot.subplots, and then actually if you run this, you're, oops, sorry. Oops. Okay. Now, so what we get here is the area where we can plot whatever we want to plot. Okay, so that's how we create the space for the figure that we're going to plot. So let's use this data that we have here, and we're gonna see what we're gonna get. So 1, 2, 3, 4, and then we have this is 1, 4, 2, 3, and then to get the plot, pyplot.show, and then if you run this cell, you get this this plot. So you can see here we have actually, if you see the plot here, the first 4 numbers are the points on X, right? This is 1, 2, 3, and 4. Okay, so and the 1, 4, 2, 3 are the white ones. 1, 4, 2, and 3. Okay, so of course we would like to plot different curves in the same plot, and we're gonna see that in a moment, how we can get different curves in the same plot. So as I said, I'm not gonna go through the details of many of these commands, but just let me show you here in this plot, because Matplotlib has something really interesting. If you see here, you have all the elements or the features that a plot should have, right? So the title, the names of the names of the axis, if you need these ticks, define these ticks. If there is a legend, if there is a grid, and for each one of these features of a plot, Matplotlib has a command. So we're gonna see how we can use these commands to create a nice plot. So how we can work with these elements, or some of these elements. I'm not gonna cover all of them. Again, this is very basic. You can do, Matplotlib has many features, so I'm gonna cover some basics. So first of all, we're gonna generate some data points. So we're gonna call x1. We're gonna use NumPy here to create some data. So with line space, we create these values or numbers between 1 and 10, and we're gonna assign the variable x1, and then for y1, y2, y3, we're gonna have the log of x1, and also the cosine of x1, and the sine of x1. Okay, yes. So actually, if you wanna check these values, for instance, for x1, these are the numbers for x1, or if you wanna see y1, y2, y3, you can see every one of them. So, and we're gonna plot. Now we're gonna plot these 3 lines. So we're gonna do again the same. Figure x equals PLT subplots. So we create the space in which, or the area in which we're gonna plot first the elements x1 and y1, and then we're gonna plot also x2 and y2. I'm sorry, x1, x2, x1, and then x1 and y3. And we're gonna show this plot. So this is what we have. So we have a plot with 3 curves, 3 lines associated to these values that we have, I don't know, created here. Okay, so next we're going to put the name of the labels of y and x. Okay, so I'm gonna work on the same one. So I'm gonna open some space here. So we have to put these commands have to be between the x.plot and plt.show. That's how Matplotlib recognizes that there is some information or some commands that have to be added in that plot. So let's say we would like to use we want to put the name of the labels of x and y. So for x, we're gonna use x.set x label, and we're gonna put here x values. And then for y, x.set y label. So you can see Matplotlib is quite descriptive in the use of the commands. So this is y values. And if we run this again, we have the name labels, of the labels of the axis. So if we want to change, for instance, the size of the text, we should put here as an argument, for instance, size, and I don't know, let's put here, for instance, 30, so we can see the difference. So you see for X values, it's 30, the size of the text. And you can do the same for the Y values, for the Y label. Also, we would like to put a legend. So we want to know, since we have 3 curves here, basically which one is which one. So what we have to do is to include here a legend. So here in the part where we plot every curve, we're going to put an argument, and we're going to put label. And label is going to be the first one, which is this the blue curve. It's the log plot, or it's a log curve. The second one, it's going to be the label. It's going to be this is for cosine. Y2 corresponds to cosine, so cosine. And for the next one, the argument would be label and sine. And we have to add here another line, which is ax.legend. And with ax.legend, we're gonna get this nice legend here on that place. So we see that every one of them corresponds to every line here, every curve here. We can also, I just said that we can change the size of the text for the labels, but we can also resize and set the resolution of the entire plot. In order to do that, we should put here as arguments for the time of, for the size of the figure. We could put, I'm going to use the same values that we have here. So 10, 10, which basically corresponds to it sets the width and the height, which is 10 and 10 inches and 10 inches. And also, we're going to use the DPI, which is the dots per, which means dots per inch, which is the density. And we're going to use 150. There is not any particular reason to use that, but so if we, okay, fixed size, I'm sorry, this is equal to, so you see the size of the figure has changed. So now it's bigger. So again, you can manipulate this as you want. If you want to have a smaller figure, or even more. But you can see that the DPI changed the density of the plot. If you compare this one, for instance, to this one, which has the original values. Okay. Of course, in a plot, we have to include the title of the plot. So actually, if you okay, let me put here the title, and it's again ax.setTitle, and then we put the name of the title, whatever title you want to use. So this is a figure with multiple lines. And then it automatically adds the title in this part of the plot. Again, you can change the size of the text, just put in an argument here, font size. So if you want to change this value, just let's say just 30, and then you see the size of the text changed. Or if you want to see this in more detail, and but I think this is too small, or 20 is fine, or just by default the one that Matplotlib uses. Also, if we want to add a grid to the plot, we just put just add this command, and then we're going to have a grid in this plot. In addition to this, we can change the values of these ticks. So for instance, well, the Matplotlib generates this automatically, but you can change the values of these ticks. So for instance, just going to change these values. Actually, you can change the values. This Matplotlib generates these values automatically. But for instance, I want to, or I would like to see some specific values. So for instance, I can set the white ticks. The ticks on the y-axis, and let's put this. Oops. Let's put the same numbers, 1, 2, 5, 6, 7. So you're gonna see that the numbers here are gonna change. So now we have 1, 2, the ticks 1, 2, 5, 6, 7. And actually this is in a log scale in Y. And also you can change the numbers, but you can put some different labels. So for instance, let's put some labels to these specific values. So for instance, the first one, let's call it 1, 2, and we can mix, we can put integers and strings, and then we have 5, and then 10, well, 10, 6, this is whatever, and then the last one. So if you run this, you see that the labels of the ticks have changed. So you can play with all of this, and that's really nice. Matplotlib allows to do many things. These are just basic things. I'm gonna remove this, so just to get this plot. So for the last part, I would like to show you how we can change here. Matplotlib automatically generates these lines, continuous lines, but we would like to change the styles of the lines and probably use markers. So for instance, let me, I'm gonna copy this and put it here. And then we can use, we're gonna add some lines, some line styles and some markers. In order to do that, we're gonna include those arguments here in the part where we plot these lines. So for instance, remember that the first one is this line, the log data. Then the second one is the cosine, and which is the orange one, and the green one is the sine. So we would like to change the log, and let's say we change this for line style. Let's say we would like to have this in this form. And for cosine, so we can differentiate even more these lines. And for instance, for this one, we use this. And let me see, for instance, for sine, we can use a marker. And this marker is going to be O. Okay, yeah. And actually, you can see here different, this is a table with different options available. So you can use whatever you want to use. So I'm using here this dotted line style. And also, well, there are many options. So you can play with that. And let's just run this plot, and this is what we get. So for log, it's the blue one. It's this. This is dash line. For cosine, we have the dot line, and the green one is sine. It's the marker. It's the circle marker. So I think right now, I think it would be interesting if you can play a little bit around with this. For instance, try to combine, because actually you can change the color of every line. So there is a hint here. So since this is a tutorial, and the idea is that you can do something else, try to change the color of, for instance, the log curve using one of these options. So for instance, you can change the color to green if you want to, or just to red. Is that an option? Yes, red. So try to do that in the next minute, and I'm going to do the same in a moment. So you're following, and I don't know if there's any question. I could try to answer any question if there is right now. So let me see.
Yeah, there was one question in Slido.
Okay.
No,
I'm sorry, I cannot see.
Well, in that case, I'll read it out to you. And it was somebody asking if the plot.show is necessary in Jupyter.
Well, actually, it's not. For instance, let's remove this plt.show, and then you get the plot, and then you get this message here. So in principle, it's not necessary. But I think this is a good practice to use plt.show, right? But in principle, no, you don't need it. I mean, you're gonna get the plot. But I think it's a good practice to use the command as it is. Okay, so for instance, let me show you. Let's change the color of the first line for red. So let's see. It didn't work. Oh, that's good. Oh. 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 So let me change this. No, it's not. Oh.
I think you've mixed color and line style, right? So maybe if you just do the dash there.
Yes. Sorry. Thanks, Kilian. I think it was you, right?
Yeah.
And then red. Now it works. Yes, thanks, Kilian. Sorry, I was mixing everything. That's good. Okay, so that's another argument. Also, you put this option in as another argument. So these are all the possibilities that you can have in Matplotlib. So again, this is a brief introduction to Matplotlib. So in the rest of this tutorial, I'm gonna go to the second part of this. I'm sorry, I'm moving this. So I'm going to go to this part, and probably binder is all, no. Okay, so sorry, just let me remove this window. It doesn't allow me to see everything. So, okay, if you open binder, and I'm working there, so you see there are some directories and there are some notebooks, and I'm gonna go through this one, which is the Higgs search, which corresponds to this chapter or episode. So I'm gonna open this one. I'm gonna close this one. And again, as I said at the beginning, if you, for any reason, have problems running this tutorial with binder, you can use Colab, Google Colab. There is a link, there is a badge here, so you can click on that, and then it's gonna open. Just be careful. Google Colab has some libraries, but unfortunately it doesn't have the libraries that we use, so you have to run some commands before you start to work. And also remember that in Google Colab you need a Gmail account. So I'm gonna, for this part, let me go through this. Okay, I think it's better like this. So I'm gonna go through this notebook, and just because of the time restrictions that we have. So as I said at the beginning, the idea in this notebook is to use some ATLAS data collected during 2016 at the Center of Mass Energy of 13 TeV, which is equivalent to 10 inverse femtobarns of integrated luminosity. And okay, and this data corresponds to the data available of the golden channel, the so-called golden channel. So we have the Higgs decaying into 4 leptons, the Higgs decays into 2C bosons, and these 2C bosons decay into 4 leptons. So this is the decay of the standard model Higgs boson. And here we have, or we will use the data available for final states with, or samples with final states with 4 leptons, and also for simulated samples and data. And we're gonna see how after applying some cuts, some selection, we will see the invariant mass peak of the Higgs boson at the 125 GeV, and that we, or the LHC, ATLAS and CMS observed in 2012. So again, as usual, we need to import the libraries that we need to use here, which are gonna be pyplot and NumPy. So we can run this line, and the samples that we're gonna use, actually, if you go through this directory, you see there are 2 directories, and the first one, we're gonna use the first one. So we're gonna have here, these 4 files have data with 4 leptons in the final state, and then we have some Monte Carlo data. So we're gonna use these files. Let me go back here to this and then close this. Okay, so the first thing that we do here is to create a dictionary with the samples that we have, and actually we're gonna use the four data samples, A, B, C, D, and the Higgs Monte Carlo samples, which are here, and all which are here. Sorry, the Higgs. This is for the data samples. This is for the Higgs Monte Carlo samples, and this is for the CC Monte Carlo samples, and this is for other Monte Carlo background components that we have. All of this is in that directory that I just showed you. We're gonna use uproot here to read the content of the samples. They are in root format. Actually, you saw this part here. They are in root format. So we're gonna use uproot to read the content of that of those samples. So if we run this, we see that every one of these files has this information, actually branches or variables in every file. So we import uproot, and then for each sample of the dictionary that we created with the data and Monte Carlo samples, we will return another dictionary, and these dictionaries are going to contain the branches or the variables of every file. So this is what we get here, and samples. Okay, let me run this again and see if for some reason didn't work. Okay, now it works. Let's look at the branches that are stored in the first file in data A. So we have here 18 branches, or 18 branches for 18 variables. And let me see, we can see or list the keys of this data. So we have the number of leptons, the mass of the 4 leptons, weights, and good leptons. We're gonna see that later. Channel number, lepton PT, good leptons, cross section, a lot of information. So with this command, let's try to access on one of these branches and make a simple plot with that branch. So we run this, and then we're gonna use the PyPlot-Hist to get the histogram, so we can visualize the distribution of the mass of the 4 leptons. And this is what we get again. PLT, for some reason it's not, let's see. PLT is not defined.
I think you need from matplotlib.pyplot import, or import matplotlib.pyplot. Oh, okay, it's there.
Yeah, it's here, but I don't know, for some reason.
I think you didn't execute it last time. I think if you just click, you just execute the first one again. This one.
Yeah. I did that. Okay, let me do it again. Actually, that twice already.
Yeah.
Let me see. And now it's okay. Yeah, I don't know. For some reason, it's weird. Okay. So here we have the histogram. This is the mass of the 4 leptons for the data A sample. And well, we could do the same for different branches, or if you want to take a look, or for different data. You're gonna play with that a little bit. So again, for instance, here, as we just saw that, you can change the size of the text. You can include here the labels, the y-axis, the x-axis, and you can play with that a little bit more. So, and actually there is an option here in which you can change the font size and the font family, and you can put this as a global setting. So actually it's gonna change everything from now. So we're gonna use it. We can get the same histogram and see the changes. So you can see this was the first one, and then we just we just resize the plot, but it's the same one, a little bit bigger. Again, you can manipulate and play these plots as you would like to. Okay, so let me go to the selection criteria of the plots. I'm sorry, the cuts that we apply here. That we can apply here in the data and in the samples and the Monte Carlo samples. And the reason to do that is that with these cuts we are able to select the events that are that are of our interest. So it's going to be a subset of the original samples. So these cuts are going to change the distribution, and this is going to help us to do some physics analysis and of course to search the physics process that we are interested in. So in the case of this 4 lepton final state, the selection or the selection or the cuts from all the samples should satisfy this criteria. The leptons need to activate either the muon or the electron trigger. The number of leptons in the final state should be 4, and the reason again is that the Higgs, we're looking for the Higgs into 2 C bosons into 2 leptons. The total net charge should be 0. The good leptons with that high transverse momentum. So we can visualize some of these requirements, and we're going to continue working with the sample data A. We can see, for instance, with this is again using uproot, how many good leptons we have in this event. So we go to the branches of data A, a good lepton, and then we get this okay, but then we can see that some of them don't satisfy this selection criteria. We have here 4 leptons, but for instance here we just have 3 leptons. Actually, we can see that here the sum of good leptons, so for instance we have 4, 4, 3, 4, 4, 4, 4, 2, 2, 4, 3. So we need only the processes in which we have only 4 leptons in the final state. So we can select all those events where the sum of leptons is equal to 4. Okay. So now in this part, I'm not going to go through the details. Almost running out of time. So in this part, we save in a dictionary all the requirements, or for all the samples, the requirements mentioned before. So the selection criteria are included here, or the codes are included here. I'm gonna just run this. Again, if you wanna go into the details, you can go through this material, but sorry, we cannot cover everything here, but, and we can compare, this is quite interesting. We can compare the number of initial and final events after the selection. So in this case, we have the initial events. And here we have the final events. So again, when we apply the codes, we would like to reduce the background events. And what we would like, what we want to do is to keep the most of the originals, or the signal that we are interested in. So as you can see, the selection for the background events are reduced after the selection, and these are in percentage. And let's see, let's plot the Monte Carlo samples. In order to plot the Monte Carlo samples, we will do stack plot. So the Monte Carlo samples are associated to the C bosons, the CC and other that I showed you at the beginning. And we have to take into account the weights, which they include important information. They modify the Monte Carlo. I'm going to go through this very quickly. And this is just to check the lengths and see that everything is okay. And this is what, I'm going to run this quickly. But this is the plots that we would like to get. Monte Carlo samples without weights on the left and with weights on the right, including the Higgs, CC, and the CCC bosons and other channels. So, so you're gonna see here two bombs around 90 GeV and another one at 125 GeV. The one corresponds to the mass of the C boson. The second one would correspond to the mass of the Higgs. Without weights and with weights. So, just to end this part, just let me run this part, and I just want to get to the final plot. But here we just take the values of the masses of the 4 leptons in every data sample in A, B, C, D. Remember that we were using only the data sample of A. But we have to include all of them, A, B, C, and D. And again, this is just to check the length of the list, if everything is okay. And we want to include uncertainties. So we need to, we would like to do, to include error bar functions. And finally, we're going to include the Monte Carlo and the data in the same figure and see if they're in agreement. They should. So this is the plot that, yeah, this is the, sorry. This is the plot where we have all the Monte Carlo and the data. Sorry, I'm going to try to reduce the size. See if we can have everything. You can see this. Okay, much better. So we have the number of events here, the mass of the 4 leptons. Remember the Higgs decaying into 2 C bosons, and then the C bosons decaying into 4 leptons. So here we have the data and the Monte Carlo here also. So again, you see 2 bonds, one in around 90 GeV, which corresponds to the mass of the C boson, and another one around 125 GeV, which corresponds to the mass of the Higgs boson. Also, where we can get this plot in a more just another format. what this would be the final plot. That was the idea to get. Again, using Atlas Open Data for the golden channel, the Higgs boson decaying into 4 leptons, and that was used to observe the Higgs boson in 2012. Unfortunately, and I knew it, I don't have enough time to talk about the mplhep. But again, you have access to all the material if you want to go through that in detail. As I said at the beginning, we use this material for the Matplotlib for high energy physics workshop. And this workshop, well, in April, it took a day and a half. So I tried to super condense many things in 1 hour, or well, less than an hour, 50 minutes. And, but again, you can go through the material. If you see any issue, you can contribute. You can go to the GitHub repo, open an issue, or just open a PR, and you can join us. We meet on Mondays, the HSF Training Working Group. We need people to keep developing these materials, and also, even if you don't have a lot of experience, you can contribute. And also just stay tuned. We're gonna have soon the second version of this workshop, the Matplotlib for high energy physics workshop. So you can participate, and you're gonna see this, all of this in more detail, and also you're gonna have time to practice, which is quite important here. So I'm gonna leave it there. I think it's time. So I don't know if there is any other question or comment.
Yeah, thanks a lot, Alex. That was a bit of a whistle-stop tour, but I think you managed to get a lot in that people will want to have a look at themselves and practice as well. So there's, at the moment, there's no questions in Slido. So if you've got one that you would like to put in there, just type away. If not, you can also just raise your hand and we can take a question.
Yeah, I'm sorry, I don't...
That's okay, I'm watching.
Yeah, sorry.
I'll let you know. Yeah.
Yeah, that's a problem with Zoom. You cannot see anything else. So.
That's right.
I mean, you can, but...
Yeah. Yeah, I mean, maybe I'll make a comment myself. I mean, just to ask you a question. So there's obviously the experiments develop a lot of experience, and for instance, root plots, which are absolutely the standard way of doing this at the moment in HEP. They're kind of like libraries of styles that you apply for this font size and this, italicization and so on and so forth. You showed us very much how to build a Matplotlib plot from the ground up, which I think is great because it gives you a lot of insight. But are there also like libraries that people have done just to apply a set of standard settings and just get kind of nice plots that you can generate quickly without having to type in every single formatting detail of the axes and the legends and so on and so forth? Yeah,
that's true. Yeah, again, the idea here is just to, since this is the material has been designed to be applying this workshop, which is it's an introduction to Matplotlib, right? So the idea is also to especially for the students, to sit down and type everything. Yeah. So that's you learn, right, when you do it by yourself. So even if you don't, you can use then libraries where they do everything for you. But again, I think it's good just once in your life to sit down and type, right?
Yeah, do it top to bottom. Yeah. Actually, Eduardo and Killian have just pointed out that this is, of course, exactly what mplhep is there for. to have the standard styles for the LHC experiment.
Yes.
And I want to add that this is actually part of the Matplotlib module. So the part that Alexander just taught really nicely, that's like the vanilla Matplotlib version. And then in one of the later parts of this lessons, we switch over to mplhep and show how you can get this consistent style with just one added line for all of your plots to really make this convenient.
Yeah. Okay, and a couple of questions appeared in Slido as well. So the first one is, how would you represent PDFs that are not histogram templates? For example, when you have the function itself, is it easy to stack those representations?
Oops. I really don't know how easy it is. Actually, we had to, the files that we are using here, we had to filter them out because there were a lot of information, and for the purpose of the workshop, we don't need that much information. So to be honest, I don't know, but I think it would be interested to see that and see if we can add that to the material. I think that's
right. Okay, that's
great.
Again,
if there are ideas like that, we will be very happy to have your help. I mean, I think Kilian is asking for the slide. Okay. Yeah.
Okay. I mean, that's probably a discussion we can also continue offline and in Slack as well. And then Eduardo was just asking if you had example analyses from LHCb as well. No. Not yet. Okay.
No, we have ATLAS and CMS.
Right.
Yes.
But we'd happy to have like different options there to maybe switch between them. But then again, I mean, for the plotting, it should be very simple, especially because the styling is easy to switch out with mplhep. So maybe for this lesson, it doesn't matter all that much.
Yeah.
Agreed. Thanks.
Okay. Thanks, Kilian, Eduardo. Okay. Thank you very much.